fractional quantum physics, but I'm a high energy theorist. And so why are we doing this? Hopefully it'll be clear pretty shortly. Secretly, this is going to be a talk about effective field theory, duality, all sorts of things that we're familiar with and very happy with as particle theorists. And it will happen to be a very nice way to organize a classic problem in condensed matter physics. So work I'm going to discuss was done with a student at UT Austin named Amir Ross, a paper that finally appeared on arXiv back in December. And well, and I guess another disclaimer before getting started. So I had hoped to be able to tell something about physics in de Sitter. And unfortunately, I just wasn't able to pull it together quite in time to come up with a polished presentation on the subject. But if you'd like to hear more about aspects of de Sitter gravity, especially in low dimensions, where you can calculate all manner of interesting radiative corrections, gravitational effects, let me know and be happy to talk more. I'm here through the end of today, and then tomorrow morning have to fly out. All right, so I'm giving a talk about fractional quantum Hall and why should you care at all. This is maybe the one of the simplest instances of strongly correlated phenomena in physics. And so to any theorist worth their salt, it's of intrinsic interest. Let me remind you what system we have in mind when we talk about fractional Hall physics. The thing that we have in mind is we take plane, and there's some electrons confined to that plane. And we subject it to a very, very strong applied magnetic field perpendicular to the plane. And of course, these electrons interact with each other via Coulomb interactions. If they're immersed in some material, there's also interactions with stuff that makes up the material. And as a first pass at this problem, you might say, well, let me neglect interactions. Let me neglect the Coulomb interaction and see what we get. Well, in that case, the electrons will form Landau levels. And the spectrum of energies that you get looks like this. So you have bands. If I apply a magnetic field, I'm going to have in mind that my system is actually finite volume. I identify the edges. And so I have some number of units of applied flux. So this is just a number of units of flux. I integrate V divided by 2 pi over there. And then I get some bands. And if my electrons are non-relativistic, these bands are equally spaced. The spacing is the applied field divided by the mass of those particles. And these bands have an enormous degeneracy. And degeneracy is the number of units of applied flux. And this lowest one, this is the lowest Landau level, and then there's excited states on top of it. And these states, they're highly degenerate. The degeneracy is extensive in the volume at fixed applied field. And because they're flat, there's nothing setting a scale for differences of energies between these states. So for instance, if we were to think about zooming in on low energy physics, say on the lowest Landau level, there's colors over here, right? So then if we do that, and say start accounting for the effective interactions, we're dealing with perturbations around a massively degenerate state whose effective Hamiltonian is 0. So the interactions are setting the only scale available in the problem, which is why this is an instance of strong coupling physics. Now, in the non-interacting problem, you can get interesting gap states of matter by dialing a chemical potential, setting a zero for your energies. If you, for instance, set your chemical potential here, then all of these states here, these are fermionic states, they'll get filled. And there's a barrier to exciting fermions of higher states of higher energy. So you'll get a gapped state whose charge, the number of filled states, is equal to n phi, number of units of flux. So what you would get there is a state where something I'll call the filling fraction nu, which is the charge of the state, divided by the number of units of flux, is just 1 in that case. And the ensuing gapped state of matter, filling fraction 1, is a realization of what's called integer quantum Hall effect. Of course, you can do this up here. That'll give you nu is equal to 2, and so on and so forth. So in this way, you can engineer models that have integer filling fraction, and they're sort of interesting in their own right if you lived 50 years ago, but that's not the venue for the talk today. The focus of today's talk is that, well, if we say zoom in on low energies and start accounting for the effect of interactions, then this highly degenerate state, this lowest Landau level, is actually split into states that have filling fractions given by, well, ratio of co-prime integers, E and Q. And there's a vast network of such states that one sees if you crank up a sufficiently large applied field. There's a very rich structure of these states. So, for instance, there's gap states with filling fractions that are like, say, 1/3, 4/11, 5/2, etc., as well as gapless states that behave like, critical effective field theories with filling fractions like nu is 1/2 or 1/4, etc. And a first task that you might think of as a theorist is to understand, why, to have some first principles description of the interacting system that would spit out, okay, what are the possible filling fractions of these states? What are the properties of those states? What are the excitations above them? If I'm gapped, are they gapped in a trivial way? Is there some TQFT that describes those states and so on? And also, if you have a gapless theory, then you would want a model, ideally, from which you could, in principle, compute critical exponents. And ideally, you'd like to organize all of these things under the same roof, rather than having a theory for one state and a different theory for another state and a different theory for yet another state. And where this is going is that I'm going to present to you, there is a parent theory that will describe essentially all known fractional Hall physics, provided that the filling fraction is within the interval 0 and 1. In that case, we can give a unified treatment of all such fractional Hall states. I don't know how interactive things are lately, but if there's any if there's any questions along the way, please don't hesitate to ask. So filling fraction between 0 and 1, you would expect to amount to splitting at the lowest Landau level, not encountering and including corrections from higher Landau levels. that the usual art, this is expected within the condensed matter community to be a good approximation that one can just think of the problem of these states as the lowest Landau level, like then accounting for some interactions. Essentially because the splitting between levels is very large at large applied field. If you crank up the field big enough, these higher Landau levels go off to the sky, they decouple, and we're just left with the lowest one. And that'll be the regime for the talk today. Now, there's an important feature of life within the lowest Landau level in the event that's preserved in the presence of a wide range of interactions, including Coulomb interactions. And that's something called a particle hole symmetry. So theoretically, it's there for lowest Landau level, but experimentally, it's also been tested to high precision. And this is a symmetry that acts on these states. What does it do from the point of view of filling fraction? It sends nu to 1 minus nu. The filling fraction here would be 1, here would be 0. These two things get flipped under particle hole symmetry. And this, as we'll see, this will be a key player in the remainder of the talk. Now, these gap states, at least the ones that have on denominator, so like these, this is a bit more complicated. The ones that have on denominator and are gapped, these are not trivially gapped states. They have a Chern-Simons effective field theory description that looks like this. So there's the Lagrangian that's minus a matrix of integers over 4 pi. And then an extra term with a vector of integers, where here A is external. That's going to be accounting for the electromagnetic field. That's where our flux is coming from. And here, what I mean by these little b's, these are dynamical U1 fields. And this is an abelian Chern-Simons gauge theory. And those are expected to give a good description of these gap states. And there's some experimental evidence now that this is really the case.
But this is not sorry my ignorance, but this does not describe, you're not used to talk about like electrons anymore. Like that are, because before you said that you had the Coulomb interactions of these electrons, and now you're replacing these electrons by some.
Well, we say we have, if we're, we have it, we tune chemical potential implicitly, so we're sitting in some gap state. We now, there's an activation barrier to make an electron. There's also an activation barrier to make anything else. But the claim is that normally you would say at very low energy, such a phase of matter is trivial. There's nothing there. And actually, that's not the case. There's a residual topological quantum field theory.
The question means for some aspects, disorder is important, like to get the plateaus. I assume it's not going to play any role in anything.
That's not going to play any role in the things that.
Then you don't get the plateaus, right?
We'll get exact plateaus.
But I mean, you can prove that it can't be. I mean, you don't get the conductivity is a continuous function of the density if you have no disorder.
But is it difficult? Hold on. So we will see. Well, there's a question of so to what Per is referring to is that there's an expectation that disorder is important for the realization of fractional Hall physics. It's important for some things, like for instance, the plateau transitions, they're critical exponents, but it's not so important for others. So bear with me, you'll see what I mean.
Okay, I'll ask again later.
Yeah, that's right. Well, you can come back to it if you want. Right, so these are really honest to God U1 fields here. A and B is an index. I imagine it runs from 1 up to some number n. This is then a U1 to the n Chern-Simons theory. There's a fundamental constraint that Chern-Simons theories have to have, which is that these this matrix of coefficients here, the Chern-Simons levels, and the components describing the coupling of those fields to an external gauge field, that all of those have to be integral. But actually, there's another constraint, which is sometimes known as spin charge, which is that the diagonal matrix elements of this guy minus the corresponding elements of the so-called T vector have to be even integers. And where does this come from? This is consistency of the underlying Chern-Simons theory that it's actually gauge invariant. It's a well-defined quantum field theory. What this is a statement that there's states in this, or there's line operators in this theory that correspond to the original microscopic electrons. And in the original theory of interacting electrons, there's a relation that the charge of any state built from those electrons minus twice the spin of that state is even. So for instance, an electron is charge 1, but spin 1/2. And what this relation guarantees is that there are so-called transparent line operators. So these are not anyons, they don't carry fractional statistics. That the transparent lines, which would include the electron, that they obey precisely this relation right here. That transparent lines have charge minus twice the spin is even.
So in the big A is a spin C connection?
Yeah, I wasn't gonna say that yet. I was gonna, yes. That means, so at the moment, that means that A is an external spin C. And the B's are honest to God U1 fields. Okay, so that's the gap states. The gapless ones, there's an existing proposed effective field theory description of these phases on the market. It goes by the name sometimes of HLR-like theories, or Halperin, Lee, and Reed, sometimes called composite fermions. And what these theories look like, they have a non-relativistic fermion coupled to some abelian Chern-Simons theory. The fermion is electrically neutral, is sometimes called, that's the composite fermion. It's not the microscopic electrons, it's some other quasi-particle like degree of freedom that's there in the infrared is the proposal. And then one is supposed to take the mass of that fermion to 0. And this proposal is very good for many things. For instance, it can predict the existence, if I deform that theory by certain relevant operators, I can generate a whole bunch of these gap states with the expected filling fractions. But it also does have some issues. It's afflicted with IR divergences in particular in this massless limit. And it also has the feature that at half filling, when there's a proposed like theory that lacks this particle hole symmetry, which one would expect to either be a symmetry of the state at half filling, because 1/2 gets sent to 1/2, or there should be more than one state at half filling, and perhaps these states are exchanged with each other.
So what's the massless non-relativistic particle?
Right, so good question. So here's psi is a complex fermion. So there's something like a dt minus chi AT psi, that's the usual time derivative term for a non-relativistic fermion. And then you can have a psi squared by 2m. I mean a limit where the effective mass parameter controlling the spatial kinetic term is being set to 0. It's usually a pretty sick limit for a non-relativistic theory. So this was the state of things until maybe a decade or so ago, when a number of authors, including Son and Ashton and Max Malitsky and friends, proposed that perhaps there should be a better theory of the half-filled state that enjoys manifest particle hole symmetry. And so this is a proposal filling. And in this theory, what one has, so in Son's model, one has a relativistic fermion called chi that has a coupling with charge 2 to a field A, little a. And then there's a mixed coupling between that field and electromagnetism. And this model, so here I would say chi does not have a direct coupling to the electromagnetic field, it's electrically neutral. We would say that is a Dirac fermion. And this theory, while it has a symmetry, well, first off, maybe it's worth mentioning, I mean, it's because the fermion has charge 2, this is a well-defined quantum field theory, it has no anomalies. It has also a discrete symmetry. It has a CT symmetry under combination charge conjugation time reversal that is playing the role of a particle hole symmetry in this context. And although in order to make that work, there's a dictionary that you need to follow to go from this theory to a prediction for filling fractions of non-relativistic states. Would mean that filling fraction of the non-relativistic state is that coming from this relativistic model plus a half. And well, the state, this model gets a couple of things right off the bat. It gets something wrong as well. So the thing that it gets right is that it has a gapless state at 0 relativistic filling, which by this would correspond to.
Sorry, is this really the Thomas term you meant to write?
This is, I have to say what Chern-Simons terms are, I have to specify a convention for the Dirac operator.
That's true.
And in this context, okay, this is the convention where into like adding a mass term would add a sign, and then integrating out the fermion would generate a one-loop Chern-Simons term that goes like that. So this is kind of the symmetric thing, rather than the usual convention that I will use a bit later, where like adding a positive mass doesn't, and integrating out the fermion doesn't lead to any one-loop normalization of Chern-Simons levels. So
That's why it's CT in there.
this is like the, if we were back in the 80s, this would be the more common scheme that one would use. For instance, in like Nanini Semenoff and such. So there's a gapless state in this model at half non-relativistic filling. And the way that this phase works is that at that filling, so the charge, the external charge for this is integral dA by 2 pi. And if we work in a configuration where this is 0, that's in a state of 0 charge and therefore 0 filling, 0 relativistic filling. That means though that then this fermion, the composite fermion, feels no magnetic flux, at least on average. But if you track what it means for there to be a large amount of applied flux, and one way of saying it is that A appears linearly in this theory, and therefore, if I look at that acts as the Lagrange multiplier, relating the charge carried by the fermion to the external flux, so you end up getting a state where the amount of charge carried by chi is very large. In fact, it's half the number of units of applied flux, but then the flux felt by the fermion is 0. In which case, what will the fermion do? Well, this is like non-relativistic quantum mechanics. If you have a system of fermions and they have a lot of charge, but they don't experience a magnetic field, you expect to get a very large Fermi surface. In this case, coupled to Chern-Simons. And that would be your candidate for the description of this. Well, that looks like a gapless state of matter. There's ripples on the Fermi surface that are massless. So that's all well and good that you get this nice gapless state of matter from this theory. However, this model can't be right because it misses some topological properties of the phase. Well, and maybe one way of saying it is that let me not worry about this particular phase itself, but let me note that in this model, there's other states other than the half-filled one. In particular, we can add a mass for the fermion along the lines of what Thomas was, what we were just chatting about a few minutes ago. And if you add a mass for the fermion, that's some relevant deformation. And depending on the sign of the mass, you can get the composite fermion realization of a fully empty state with 0 filling, or a fully filled one with filling 1. But these have a residual TQFT description, where effectively you replace the fermion just by a Chern-Simons term. And I guess I got my signs wrong. I think it's plus minus 2 squared. Yeah, no, just that sign of mass divided by 4 pi ADA minus 1/2 ADA. And this should be an 8, sorry. And thanks to the wonderful properties of 2 squared over, the 2 squared is just coming because the fermion carries charge 2. And then the sign of mass over 8 pi, that's the usual radiative correction for Chern-Simons levels at 1 loop. This becomes, I can write this as a 2 over 4. And what we see is we have a residual U1 level plus or minus 2 Chern-Simons theory in the infrared. Meaning that this model makes a prediction that it has a fully filled, fully empty state that have some residual topological order, as opposed to just being trivial. That's a bad problem. That's enough to kill this as a viable theory of the half-filled state. So a little bit later, next year, there's a lot of effort studying related problems in the context of 3D bosonization dualities. comment more on those in a moment. So see also, Art and Tong. A lovely paper by Seiberg, Sentil, Wang, and Witten, where, well, their main interest was looking at the analog of Bosenization, but in 2+1 dimensions. So they wrote down along the way a candidate theory that's and you can think of it as an improved version of Sans. And this theory, what is it? Well, it has a fermion chi. It has a coupling to a field I'm going to call little a, but this time with charge 1. Minus 1 over 2 to a d b. There's another field. I'm going to call it b. Minus 2 over 4 pi b db. And then a minus 1/2 b dA. And they propose this as an improved version of Sans theory. It's a candidate description of the half-filled state. And therein, there's no need for a dictionary anymore that relates the filling fraction observed in this theory to a non-relativistic one. And when I write down this Lagrangian, I'm working in a convention that adding a large positive mass for chi and then integrating it out generates no ADA, but then adding a large negative mass in the infrared would generate a plus ADA by 4 pi. That's my convention for the Chern-Simons levels. And this model, this is an improvement. It gets the same things right that Sans model did. So at half filling, the flux, well, so you have to track things through a little bit. At half filling, that fixes the flux for B, and then that in turn, through the coupling to A, fixes how much flux there is for A. That ends up being 0. So the fermion chi feels no flux, but then the condition that we have half filling fixes the charge of chi to actually be the number of units of flux divided by 2 again. So just like in Sans model, we have a state of matter that is described by a very large Fermi surface coupled to Chern-Simons. I guess I should also say this model has an anomalous version of CT, which is playing the role of particle hole. And it's anomalous in the sense that if I couple it to a 3+1 dimensional topological insulator, then I have an honest to God CT symmetry. And if I track what this symmetry does to the filling fraction, it exactly does what I want it to. It sends it to 1 minus nu. So that really is a good candidate for particle hole. The other thing that it does, besides getting the gapless state at half filling right, is it has the analog of fully empty and fully filled states. The fully empty one comes from a very large positive mass deformation, or adding a Dirac mass to the fermion. The fully empty one from a large negative mass deformation. And in both of these cases, in the deep infrared, you get a trivially gapped phase. No topological order.
Can I just ask about the net flux being 0?
Yeah,
Like,
yeah.
that was just being like a subsector of the theory, basically.
That's a state you should think. That's right. Yeah. So I mean, if I want, I can. It's just fixed. Looking in the sector of fixed charge. Right. So what I wanted to do was, and I guess I'll have to speed up a little bit, is to show that this model, this kind of improved version of the half-filled state, does a lot more. In fact, it provides a unified description of the whole, all the states I was describing earlier within the first Landau level. It has a very complicated, in other words, landscape of critical points and vacua. And I don't need disorder to get it, that's the connection with disorder, so. Let's keep going. How does this work? So. Okay, so. What else is there? Well. We said that moments ago that at half filling. That fixes the flux of B, that in turn fixes the flux of A to be 0. One can study other states where the flux of A is something else. In other words, we can ask what happens if chi feels some flux, in particular, some large amount of flux. And what'll happen in that case is that, well, what'll happen is that you expect then your chi to form Landau levels itself. And then the coupling to Chern-Simons fields would be some extra interactions on top of those. So you'll end up with a spectrum of Landau levels for chi. Since it's direct, that network of Landau levels goes both up and down. There's a one right here I'll call the lowest one. Call that n equals 0, n equals 1, n equals 2, n equals -1, n is -2. And the ensuing model will have vacua if if my effective chemical potential for the fermion is such that I'm sitting in a gap in between these Landau levels for pi. So say I'm sitting right here. Or if I'm sitting right here, right here. And if I'm sitting in such a gap, then, well, assuming that the gap is large compared to other scales in the problem, we'll return to in a moment, then I can integrate out the fermion and replace it. I'm just in some gap state, just a number of filled Landau levels. I can effectively replace the fermion with a Chern-Simons term describing the response of the filled Landau levels to perturbations of A, the field that's coupling to it. And well, if I'm here, the response that I would get is ADA by 4 pi. Here it's 2 ADA by 4 pi. Here it's 0. Here it's minus ADA by 4 pi, etc. In other words, in such a gap in the spectrum, I can replace effectively this by n ADA by 4 pi, a level n Chern-Simons term for A. And if you work out what the resulting filling fraction of the state is, this looks like an abelian Chern-Simons theory, after all, we can compute the filling fraction for it. You'll end up with a filling fraction that's fractional, n over 2n plus 1, where here n can be 0 as well as positive and negative. So back over here, you can write down what the corresponding filling fractions are. This one is n equals 1. If I plug n equals 1 into that formula, I get a state of a third filling. Up here, 2/5. Here, 0. Here, -1. -1 over -1 is 1. Here would be 2/3, and so on and so forth. And if you look at these numbers, one thing screams out. Well, they include 0 and 1, but they also include non-trivial fractions, which is what we expected from before. Moreover, 0 and 1, 1/3 and 2/3, 2/5. Next one down here is 3/5. There's a manifest particle hole symmetry here that flips things down here with things up here. There's our particle hole. And we get a whole bunch of gap states this way. These are not new to this work. These were known for ages. These are called Jane sequences. And, well, they have these states, if you go and look in the condensed matter literature, it's an expected trial wave function that's a good candidate for the ground state, for these many body states. And from that trial wave function, one can extract an effective Chern-Simons description with the K matrix that looks like this. This is expected. Would expect it to be, I'm going to write it for n bigger than 0. Looks like this. It has n entries, or n absolute value entries. It is, for n positive, it has 3s down the diagonal and 2s off the diagonal. And in terms of a general Chern-Simons theory, where I have this TA that I talked about earlier, this will be 1, 1, 1, then 1, at the bottom. And between that, put some dots. And, well, if we go ahead and look at the theory that we just constructed, it's the TQFT here, it's not like this. This is something that has 2 fields, not n. And it has an effective K matrix that looks like 2 minus 1 minus, or 2 plus 1 plus 1, and then minus n, where this entry here is B and A, and then the T matrix here, or sorry, T vector, is 1, 0. So what gives? And furthermore, if you look at this a little bit, you'll notice that before we said that there was a spin charge relation that had to be satisfied. So the diagonal elements of the K matrix minus the corresponding element of the T vector had to be an even integer. And here, well, that is 2 minus 1 is not, that's not an even integer. And 0, or so minus n minus 0 is, well, might be even or not, depending on whether n is even or not. And you might say at this point, oh no, we've really screwed something up. We have something that predicts filling fractions for known fractional Hall states, but we're not getting the effective field theory right. However, that's not the case, mercifully. In fact, there's a way to do something like Hubbard-Stratonovich to go from this description to this description. But in order to do that, we need to account for a subtle feature of these Chern-Simons theories that Thomas already noticed earlier in the context of the background U1 field, which is, so there's U1 fields, standard U1 fields that obey a standard normalization condition on their fluxes. If I notate that fields as B, their fluxes are integral. There are other kinds of fields that we care about in settings like this that are called spin C fields, which are locally like ordinary U1 fields, but globally their quantization of fluxes is a little bit different. Particular, so I'll call such fields A, and their flux plus a half of an offset integral of the second Stiefel-Litny class. This thing is quantized if little a is a spin C field. And here, when I wrote down this effective action, secretly what I had in mind was that A was such a spin C field. So if I was just interested in doing like perturbation theory and drawing diagrams, I wouldn't care about this. But for problems like the statistics of line operators, I have to worry about it. And right, and what this effectively does is that this modifies the spin and the statistics of line operators that involve a coupling to A. Well, as well as more generally. And so a convenient way to tackle this is basically to replace a Chern-Simons term for A with something else. And replace this with a, by integrating in absolute value n ordinary U1 fields. I'll call them C. And then there's a coupling between A and C. U1 level 1, and these individually, these C's, they're U1 level 1 fields. Quantum mechanically, that means that they're trivial as quantum field theories. A U1 level 1 theory on any compact space has a single state in its Hilbert space. So you can, in other words, to go from this to this, you can just integrate out the C's in the ordinary way, and you'll get this out of it. But if I allow this replacement, step it in here, what do we get? Well, we get minus, this is a computation we can do on the board together, so it's really worth it to walk through that computation. So what we notice now is that A appears linearly in this effective action, which means it acts as a Lagrange multiplier, and we can integrate it out. And what it does is it sets this flux of B to be the flux of all that of the C's put together. And if we simplify things and now the Chern-Simons term BDB becomes a Chern-Simons term for the C's, and it equips the external field A with a coupling to the C's. The resulting Chern-Simons theory that we get is exactly this right here on the nose. The 2's come from this 2, and then the diagonal entries, 3 is 2 plus 1. This is the 1, and then there's an extra contribution of 2 from here. It's the way that it works. So in fact, this theory that we wrote down initially, thanks to the fact that A is spin C and all this other jazz, it actually obeys A, the spin charge relation, and also reproduces the expected TQFT description of these Jane states. So far, so good. These Jane.
Oh, is there also an expectation for the thermal Hall conductor?
Oh, yes, yeah. And that requires a little bit more discussion as well. That has to do with the so what Thomas is referring to, so far I've discussed this theory in flat space, but we can successfully couple this model to gravity. And when you do that, and say the simplest way, the way that I know how to talk about thermal Hall conductance is to then take a system like this and study it with a boundary, with an edge. And then there, in that context, there will be some degrees of freedom that are localized to the edge, some edge modes, which you can think of as describing a chiral CFT that has some asymmetry and some non-zero chiral central charge associated with it that can be computed from the bulk K matrix. And there are basically, long story short, it all works out. You match standard expectations. Okay, so you also match something else if you've ever heard of the Wenzel shift. That also matches on the nose from this.
Given that it matches, maybe you can explain what it is.
Can because I have maybe 10 minutes, I wanted to, I can tell you more afterward, but I did want to get to, so these.
I didn't mean as a matter of definition, I know how it's defined. You've been giving the talk from a high energy point of view.
Right.
You talked about two things that have a nice interpretation as a relativistic Chern-Simons.
Yes.
The Wenzel term does not.
Yeah. Let me talk after, yeah, maybe if anyone else is interested in hanging around, then we can keep talking about after. I want to, so far I've gotten a bunch of excited states, or a bunch of gap states, this way. But we can get a lot of other gapless points and a lot of other gapped ones as well, provided that we exploit, this is where the extra fun comes in, three-dimensional dualities. So there's a lot to be said about 3D dualities in general, but for the purpose of this talk, we said if this composite fermion pi feels some applied field, there are gap states where the fermion feels some field, but we're effectively in between some of its Landau levels. I guess I should have mentioned too that the spacing for these things is quite large. It goes like, thanks to the fact that these are Dirac fermions, the spacing goes like the square root of the effective field that is felt by the fermions. And one can show that this is of order square root the applied field divided by the denominator of the filling fraction that one experiences there, which in this context would be 2n plus 1. So these gaps are quite large initially, and then they get kind of smaller as you go further up and down. And once they become so small, then other interactions and effects that we've neglected will be of comparable strength, and the picture that I've described will break down. So this thing is best kind of for quote unquote small n. But there's other states, this is what I'm getting at, where say a single level might be partially filled, as opposed to sitting in between levels. And in that case, what are we dealing with? Well, we have a partially filled level plus interactions. Well, we're back to the same sort of problem that we started with that enjoys it's strongly correlated. It's a partially filled level. The interactions set the only scale for energy differences. They set the effective Hamiltonian for that level. But in such a state, say we filled the partially filled the -1th level, and we have just do a little magic here for a moment. So in that case, we can effectively replace this fermion by the actually let me go down to, yeah, I can replace it by the response from down here, which will be -1 by 4 pi AdA. And then there's a fermion itself in the level. Maybe I shouldn't call it the same name, I'll call it something else like Ada or something. Describing the partially filled fermion in the level. And what we can do at that point is we can use one of these known three-dimensional dualities to trade out this fermion eta for a new fermion, I'll call it psi, along with two additional statistical fields. If I call these A1 and B1, then one of these dualities that I was alluding to earlier from this paper of Senthal, Seiberg, Wang and Witten, what does it do? It says that I can trade a free fermion eta plus a level 1 background transition for A, that this is equivalent to a new fermion psi coupled to a new field A and B. Like this. And well, let me do exactly such an operation here. I'll trade out this fermion here for a dual description in terms of a new fermion psi plus a couple of extra fields that I have to integrate over. And when I do that, let's see. I think I might have gotten, did I get my signs wrong a little bit here? Let me just consult my notes for a moment. Oh, sorry. You know what I wanted? Okay. In general, I would, if I partially filled the nth level, I don't know why I said -1. I had in mind partially filling n equals 1 instead. So let me I'll partially fill the first level just for fun. Then I have 1/4 pi plus the partially filled levels response. Then what happens is, well, I replace this by this. I end up with a new theory that is psi bar d / coupling to a new statistical field A2 minus 1/2 pi A2 dB2 minus 2/4 pi B2 dB2 1/2 pi B2 dA1. But then there's all the fields that were left behind. Minus 1/2 pi A1 dB1 minus 2/4 pi B1 dB1 and a plus 1/2 pi B1 dA. And for the particular case where I just fill up the one level, I just dualize the second line, I have nothing else left. If I build some other Landau levels as well, then there would be some extra residual Chern-Simons term for A1 left around. But this case is special. And we can see that it's special. We have a new composite fermion psi that couples to A2. A2 still does some other stuff in here, but if I look at the field A1, say in this Lagrangian, it appears linearly. And just in those two terms right there. You can check yourself, it appears nowhere else. And so even in this model with the fermion lying around, we can integrate out A1. It implies that up to gauge transformations, B1 and B2 are coincident. And when we do that, we can get, well, we just have A2 left. I'll call that A. We have a minus 1/2 pi AdB. These two terms double up. You get a minus 4/4 pi B dB. I'm just calling B. Oh, B1 and B2 are the same. We get this. And this looks an awful lot like the Did I get them all? So this I integrated out, this and this doubled up, that became this, and that are left over. That's that on that. I think I got them all. Simply only do simple algebra in talks. So this looks an awful lot like the SSW theory, except this 2 has been replaced by 4. And that has a couple of significant effects. One of those effects is that now this new model has a gapless point at a different filling fraction than a half. Now this has a gapless point when again the statistical flux for A is 0. And if you track through what the filling fraction is, that implies that the filling fraction is actually a quarter instead of a half. Same kind of idea, and it's described by, again, a Fermi surface coupled to Chern-Simons. So you get a new gapless point, but you get more than that. You also get new gap states when the field psi, the fermion psi, feels some flux A, forms Landau levels, some number of which are totally filled or totally depleted. And the gap states that you get have filling fraction, and we call the number of filled levels for psi m, look like this. The picture that you get, I'll write it for here. So this state right here, this was a third, this was 0. What we end up getting m is 1, m is 0, m is 2, m is -1. So here we get nothing. This is m is 0. This one right here, we get 1/5. At -1, we get a third. Up here, we have 2/9. And then it's -2. We get 2/7. Goes up and down. And all these numbers that we get end up living in the interval between 0 and a third, actually. Which, if we went back to our original description, the level that we're partially filling was sandwiched in between the nu equals a third state and the nu equals 0 state. So in other words, what we effectively did by performing a duality operation was we blew up this strongly correlated partially filled level into this network of states. And let's say, okay, these states, these are the so-called. These also have a expectation in the condensed matter literature. These are some other so-called Jane sequences emanating from a gapless state at a quarter filling. What we've seen is that all these states live within one and the same model. But in order to uncover them, we have to perform some duality operation. You can go ahead and continue and find the TQFT description of these gap states. It coincides with expectations. You can perform duality as many number of times you want. You get increasingly complex and fragile states of matter, but you reproduce the entire known landscape of fractional Hall states with filling between 0 and 1 this way. And again, I want to stress coming from one and the same theory.
Can you see this? Like, I mean, it seems like you could do some sort of spectroscopy on this, like, in this filling level. Can you see this in an experiment somehow? Or?
Oh, that these things, that this is the right description of the, there is some, how to say, that's a good question. There is, let's see, there, yeah, in particular, I think it's ARPES is the name for it. You can do some ARPES spectroscopy of fractional Hall states. And the question, like, is really, you know, do you see, for instance, like a Fermi surface at a quarter filling or half filling or what have you? That's difficult to do in general. It's usually easier just to look at the, like the electromagnetic response of those states. And there's some data, I think it's consistent with what I'm drawing here. I mean, there's saying I have a Fermi surface coupled to Chern-Simons leaves a lot of wiggle room because the Fermi surface is described by a lot of Landau parameters. And to fully specify what you mean by the theory of the Fermi surface, you need to specify those parameters. You can think of those as margin, like when we say Fermi surface coupled to marginal Chern-Simons, I'm describing a whole conformal manifold of possible theories. I don't know exactly which one I've landed on. Like for some choice of Landau parameters, yeah, these spectroscopic experiments are consistent with that at half filling. Quarter filling is a little harder. There's some property of response curves that I know could tell you a little bit more about that's consistent with what I'm saying, but it's a bit harder to get a direct handle on it. Okay, I've gone over time, so let me wrap up with an extra statement. So in the way that I've described, you get a vast landscape of critical points, like quarter filling, that are glorified, always even denominator Fermi surface coupled to some Chern-Simons theory, as well as gap states with odd denominator filling. Those gap states are always described by abelian Chern-Simons theories. One can also get gap states at even denominator filling as well. And the way that you can do that is by taking this Fermi surface coupled to Chern-Simons. So for instance, if we were at a half filling again, so let me remind you, we have I d chi minus 1/2 over 2 pi ABB minus 2 over 4 pi BBB plus BDA. Well, I'm writing down sort of the most, just the marginal and relevant operators for this thing. But if you have, for instance, I to the 4 deformations, say that are generated in the RG flow that takes us to this low energy phase, then these kind of the 4 interactions can generate pairing instabilities of the ensuing Fermi surface. And well, if I have a Fermi surface that's, Fermi surfaces are typically very robust against interactions, with the exception of pairing instabilities, which can destabilize them and you get a superconducting phase at low energy. And depending on the nature of like the quantum numbers of your potential pairing instability, you get different superconducting phases, except they're also coupled to Chern-Simons. So the net result from all this, and I apologize for being schematic, I'm rushing here at the end, is that you end up with a non-abelian topological superconductor at low energies, so non-abelian TQFT in the infrared. So for instance, if I take the nu equals a quarter state, which I recorded on my notes, and I destabilize it with an S wave pairing, the low energy TQFT that you get is the Ising TQFT cross a U1 level minus 16 divided by a common Z2. And you can get similar results for other arbitrarily complicated even denominator fillings and where you consider other quantum numbers for the pairing. And the punchline of this is then this technology gives you proposed descriptions of gap states with even denominator. For instance, if I were to add to this 2 spectator Landau levels, this gives me a proposed description for the 9 quarters state. Or if I were to do this at a half filling, I can get a description of the 5/2 state, and in fact matches the expected one. So with that, I'll thank you very much for your attention.
When you said that these states are more and more unstable, you're referring to this instability or the fact that, like, is the regime of validity getting?
Yeah, there's implicitly, I mean, I'm writing down the most important operators, but there should always be understood to be some ... dots hiding in the wings suppressed by some energy scale. And this picture is valid to the extent that these inner Landau level gaps are large compared to those scales. And because these gaps are controllably large, I can get a regime of validity that holds, provided that these scales themselves don't scale with the applied field.
Well, 5 halves, you get more read.
You get T, well, if you do the S wave, you get this thing called T Fathian, which is like a particle hole symmetric version of the Fathian state.
So what do you have to condense to get?
I think it's the. Oh, I don't remember. Well, I think actually, I'm not sure, come to think of it, that you can get more, I think you need actually some extra decoupled sector to get more read. Right, which is eluding me as I'm standing up here, but.
Like some massless, something massless.
No, I mean, okay, let me, so. Let me back up, maybe to frame the answer, so. In the gap states I presented at odd denominator filling,
Right.
you end up with very simple abelian TQFTs. There are known proposals that there's proposals for states that have that would also be candidate descriptions of, say, the 411th state that are what I wrote down plus more. Extra fields, extra line operators. And at the level of line operators, they can always be written as the line operators of the abelian theory that I wrote down, plus some extra ones that commute with all of those. And what I'm saying with more read is, I think in order to get like, it's not just that I can't realize more read if memory serves from this theory. I actually need other line operators in order to get it.
Maybe I question this is close to the Fermion theory originally,
Yes.
and then effectively described it with the transfer theory, like with a single copy of one originally first, just the photon only. How does the
Sorry, you said the 2 + 1 dimension. Oh, so then the non-relativistic fermions that I imagined in the first place, because they're non-relativistic, they don't have any
but then the Walter Simons theory has the
are you referring to the fact that if I introduced an edge, that the edge theory would carry an Tuft anomaly?
I mean, even without edge, yes, well, the photon, the Yuan-Simons theory has the photon only in a sense that they do on.
No, yeah, sorry, I see what you're saying now. Good. So, right, so these theories have okay. Good. That's what you're talking about. Let me tell you something. So what you're asking about these so here's our abelian Chern-Simons theory that we started with. And depending on what K is, this theory can have one form symmetry. So for instance, let's just take a very simple case. Let's take a case where there's only one such field. Then what you can do is, and say the level is 3. So then if we're on a spatial torus, then we can shift B to B plus a large gauge transformation around one of the cycles of the torus divided by 3. And that's a one form symmetry of this theory. And as you said, that the one form symmetry is anomalous. There's no obstruction to quantization of this theory, of course, it's an Tuft anomaly, as you said. You could ask, does this anomalous one form symmetry, does it match anything in the ultraviolet as the Tuft anomalies usually do? The answer is yes, it does. So microscopically, what we had in mind was electrons in an applied field. For which, if we think about for a moment, we're living on a torus, say. Then, and it's threaded with some magnetic flux. You have in mind, so I have in mind, at least for this, a model that has originally translationally invariant interactions, no disorder. And in that case, if I have translationally invariant interactions, the magnetic field actually breaks those translations to a subgroup. There's no longer continuous translations that preserve the field. One way of thinking about this is that you could say like AX is BY. And then this is no longer invariant under continuous translations in Y. But you end up with if there's n phi units of flux, there's a projectively realized algebra of so-called magnetic translations. There's a length scale that you can construct from the applied field, and basically you can translate by x, some x plus a magnetic length, and similarly, there's a translation in y by a magnetic length divided by some amount, by some amount that, okay, and I have in mind, I guess, when I'm writing here for a square torus. We can generalize it for a non-square torus. Anyway, these Tx and Ty, because of the underlying magnetic field, they don't commute with each other. Tx, Ty is e to the 2 pi I nu Ty Tx. This is the usual Heisenberg algebra of magnetic translations. In this case, the phase that I'm dealing with has a third filling. And what happens here then is that Tx and Ty cubed commute with each other. But Tx and Ty themselves have this Heisenberg algebra. And then what's matched, and maybe you see it now in the TQFT description, the operators that are charged under the one form symmetry are the line operators of B around the X and Y cycles of the torus. And they, thanks to this one form symmetry, obey exactly the same projectively realized algebra. And that's true in this very simple instance where there's a single field and level 3, but it persists more generally for the landscape of theories that I wrote down. So in general, whenever you have this, you in general have a one form symmetry that I write the filling is P by Q. The one form symmetry is in general ZQ. And what is it there to do? What's its role in life? It's realizing the infrared version of the anomaly or the projectively realized translations in the ultraviolet.
Got it.
We should thank Kristan again.
Thank you.